All right, guys. Good morning. So I'm gonna be taking off again today. I already got my email, most likely, hopefully. Today we're gonna be going through the notes for 3.2, which deal with measures of variation. So what do I mean by measures of variation? Well, imagine you have a dot plot of a data set. Okay, there's our x-axis. Let's say my data looks like. Oh, it froze on me. Weird. Maybe it's got to do with this light. Yeah, whatever. Okay, so imagine that this is the data set. I'm just making something up, right? Something like that. And then on the same axis, on the same scale, we have another data set. Look at that face that it froze on. Can I get that out of the way? You get that out of the way. That's a little funny. I like that one. Let's get one more time. All right, so let's imagine I have another distribution. I'll just do it in blue. No, you can't really tell the difference. Let me try red. Yeah, that's a little bit better. So imagine that the other distribution looks looks like that. Okay, so one of these distributions is very spread out, right? And the other distribution, well, really isn't. So the whole idea about measures of variation is to tell like how spread out or how concentrated a distribution is and the various ways that we can describe that numerically instead of being like hand wavy. It's nice to be able to compare things and whatnot. Okay, so let's go ahead and get started into the notes. Okay, the easiest measure of variation that we probably are already familiar with is called range. Okay, that's very, very easy. That's the highest value minus the lowest value, or the min minus the max. Okay, so yeah, range is equal to max minus the min. So let's do that real quick. Data show the sample for top grossing movies and millions of dollars for a recent year. Find the range. Well, that's certainly not this year, right? Okay. So the max would be, looks like 409. The min would be 70. So 409 minus 70. What's 409 minus 70? Oh, geez. 339. It's amazing like how much cognitive ability decreases when there's just some level of background pain. You know, like everything falls apart. Like I have like I would say between a 2 and a 6 level pain in my leg and back, and I'm like walking into walls. I'm like trying to add numbers and like I can't do it anyway. All right, so data variation. So the difference between each data value and the mean is called a variation. Okay, that variation can occur within the population or it can occur within a sample, right? So some value of x, right? Some random variable x, you subtract the population mean, or perhaps you have a sample, so we're taking some data value, some instance of x, and you're subtracting x bar from it. This is known as variation. Okay. So find each deviation in the given sample set. Well, variation, deviation, they throw those words back and forth a lot. They basically mean the essential same thing. Variance is not the same thing as variation, so be careful when we talk about variance. We're talking about something very specific. Okay, so find the deviation in the given sample set. So first thing you have to do is calculate. This is a sample, so we'll be using x bar. First, we have to calculate x bar. So x bar would be what, 10, 70, 120, 150, 190, 210. divided by 1, 2, 3, 4, 5, divided by 6. That's 210 divided by 6. That's 35. Okay. So let's make a little table. Make a column for my values. And then I'll have this be x minus x bar. So this is the value. This is the deviation or the variation. So let's just go ahead and copy this down. I have 10, I have 60, I have 50, 30, 40, and 20. All right, so 10 minus 35 is going to be negative 25. 60 minus 35 is 25. 50 minus 35 is 15. Negative 5. Right, 5. And then I have negative 15. Okay, so the sum of the deviations in a data set, which we would write as using our sigma notation, always equals, well, what? Let's see. Well, 15, 20, this adds up to 0. That will add up to 0, and this adds up to, so they all cancel each other out. Does that make any sense? Well, yeah, think about it. If the mean is the balance point for the distribution of a data set, like imagine this is a seesaw. Hopefully you guys had a decent enough childhood where you had seesaws, right? So the mean, remember, is like kind of where it balances all the distribution is, like right there, right? So if you think about it this way, what the mean does is it finds a balance point so that all of these points or weights or data values, right, are in balance or cancel out all of these. Otherwise, the force of gravity, if this were a seesaw, would pull it one way or the other, right? And I would have an unbalance and I would end up with something which is not in equilibrium. So it's a nice physical example of what a mean is and why it does. If you do find the variance, so the variation or deviation from the mean, it does always equal 0. So in order to eliminate this problem, instead of looking at just these differences, we sum the squares of the deviation. It's like basically finding a magnitude or absolute value, sort of. Okay. So this brings us to the conversation about variance and standard deviation, the essential descriptor for spread. Okay, so oops. The population variance is the sum of the square deviations divided by the number of terms in the population. Okay, so we don't usually calculate this because we don't usually calculate things for populations. Oh, I realized I was so out of focus. Sorry. Come on, you guy. That's certainly not in focus. Focus. All right, unlock that up. Okay. All right, so what's that look like? If we talk about population variance, we use this symbol sigma. This is lowercase sigma. So sigma squared. Variance is squared. All right, so it's the sum of all of these differences. Remember, it's populations. We're using mu. We divide that by capital N for the size of the population. Okay, so let's just make sure we define all these terms. Okay, this is equal to the variance. And this is, of course, for population. Okay, we already know that this is equal to the mean of the population. Okay, and we know that capital N is the population size. Okay, so this has its analog for samples. and this is called sample variance. Okay, instead of using lowercase sigma, we use the English version, which is an S, and it's still squared. Everything looks exactly the same, except you're using the sample, not the, so I'm talking right at the same time. You're using the sample mean and the sample size. Okay, so I'll write it down anyway. That's equal to the sample variance sample mean, and n is of course sample size. Okay, now what we usually talk about is not variance, whether it be population or sample, but we usually talk about the standard deviation. And to find the standard deviation, we simply just take the square root of the variance. That's it. Okay, so this is a quick rundown. To find population standard deviation, you have to find the mean of the data values. Okay, find the deviation of each, and in order to do that, well, let's run down. So find the mean, find the deviation of each value. You square each of the deviations. You sum those squares, divide that by the size of the population, then you take the square root of it. So don't worry, we're going to use technology to do this the vast majority of the time. I'll show you how to do this using sheets when we get around to it. I'm not in any particular rush. Let's make sure we get these skills down first, and then we'll start working with our calculators. You should all have those Inspire CASs or the CXs, and they make this some pretty short work. In either case, let's just do it by hand a couple times so we can at least appreciate what that computer and calculator are doing for us. All right. So let's write these down. 10, 60, 50, 30, 40, 20. Okay. Find the population variance and population standard deviation for the data set. Okay, that's easy enough. So first thing we do is calculate the mean. This is a population. It's a very small population, but it can be a population. It all depends on how you define it. So I should have my calculator. I do have it on me right here. It's right here. So let's go ahead and just do that now. Might as well. Make short work of this mean. Probably just do it in our heads real quick. 10, 70, 120, 150. Oh, it's 210 again. Okay. Did I do this wrong? No, wait. That's 210, right? 210 divided by 6. It's still 35. Okay, so now I have 10 minus 35. That's going to be 10 minus 35 is going to be negative 25. I think I just did this. 60 minus 35 is going to be 25. Yeah, but this is the same data set. That's negative. That's positive. And that's negative. Okay. So then we got to square these. Negative 25 squared is 625. That's also 625. That's 225. That's 25. Okay. All right, so let's add these up. Okay, if you add up all of these, you will get 1750. So the sum of x minus mu squared is equal to 1750. Okay. So population variance is equal to That, well, I might as well just write it. So that's 1750 divided by 6. Turns out to be 291.7. And that's the variance. And if I want standard deviation, all I have to do is square root that. So the standard deviation is equal to the square root of 291.7, which turns out to be 17.1. So this is the important part. What does this number mean? What does it actually tell me? Well, it tells me this. It tells me how much each of these data sets on average differ from the mean. Okay, so I'll say it one more time. This number, standard deviation, is how much on average each of these differs from the mean. Okay. All right, I want you guys to try to do this one on your own. Pause the video and then come check with how we did it. Okay, if you did this correctly, you should have gotten these values. This is the exact same thing that we just did. Okay, so you should have gotten those values. I'll just sit there for a second. There's no real need to sum the x's. I don't see the point of summing the x's. Okay, unless of course you're just going to be trying to solve for the mean. I guess that makes sense. Yeah, you're solving for the mean there. All right, so let's see how we can get. Now that we've done this a couple times by hand, let's see if we can do it with. Actually, no, we're going to do it one more time using standard deviation for a sample set. Okay. Sorry, as I was trying to explain to you, I'm not running on all cylinders, as they say, at the moment. Okay. So the only difference between the population standard deviation and the sample standard deviation, besides the notation, where you're using S instead of sigma, is we divide by n minus 1 instead of n. Now, the reason for this is not just because someone decided that. All of these calculations derive from calculus and calculus derivations of distributions of how we would define theoretical distributions. And it's something that is pretty cool to do, but it's obviously beyond the scope of this class. I just want you to know that this n minus 1 is not arbitrary. It's a solution derived from calculus. Okay, and if you know anything about derivatives, that minus 1 might look familiar. So the number of students admitted into an Ivy League schools from random sample of local high schools is shown. Find the sample standard deviation. Find the sample standard variance and standard deviation. Okay, well, let's go ahead and do that. First is write down all the numbers here. It's 9, 10, 14, 7, 8, and 3. All right, we need to calculate x bar. Might as well find the sum here. 19, 23, 30, 38, 41. Did I mess up? Yeah, it should be 51. Okay. So now we're going to find the mean. One, two, three, four, five, six again. Okay, that means 51 divided by 6. Is my thing up and running yet? Okay, so we'll learn how to do all of them soon. Maybe today, if it seems advantageous. All right, it's 8.5. Okay, so 9 minus 8.5 is 0.5, 10, it's 1.5, 14, that's 5.5, told you, brains fried. All right, negative 1.5, negative 0.5, and then negative 5.5. Those are our differences. Now let's square them. 0.25, 2.25, 30.25, 2.25 again, and now we're looking at just repeats. Okay, of course, what should this sum up to? This should sum to 0, and this sum of x minus x bar is going to equal 65.5. Okay, so s squared, not sigma squared, right, is going to equal the sum of the difference of the squares over n minus 1, remember, that's the big difference, right? So that's 65.5 divided by n here is 6, so 6 minus 1, which is 5. Okay, so s squared turns out to be 13.1, and so square root that, and s is 3.6. Standard deviation is 3.6. So on average, these data values will differ from the mean by 3.6. Okay, so let's read through this together. As previously stated, variances and standard deviations can be used to determine the spread of the data. If the variance or standard deviation is large, the data are more dispersed. This information is useful in comparing two or more data sets to determine which is most variable, right? If you have a low standard deviation, that's high consistency. If you have a high standard deviation, well, that means that you have a lot of variability in your output. And so, depending on what you're looking for, that can tell you a lot. Okay, the measures of variance and standard deviation are used to determine the consistency of a variable. For example, in the manufacture of fittings, such as nuts and bolts, the variation in diameters must be very small, or the parts will not fit together. The variance and standard deviation are used to determine the number of data values that fall within a specified interval in a distribution. Okay, now we start talking about, well, I guess you'll see probability distributions, which are really powerful. So, for example, Chebyshev's theorem, which we will talk about a little bit, shows that for any distribution, at least 75% of the data values will fall within 2 standard deviations of the mean. Which is why, when I understand that there were crazy circumstances this year, but when we observe what's the exact line I'm looking for? When we observe voting counts, right, for the election of this past year, the presidential election, we observed in a lot of counties voting counts that were 5 standard deviations above the mean. 5 standard deviations above the mean, and that's so crazy. Like it's possible. Anything's possible, right? And this is the first time we've ever done unsolicited mail-in ballots to everybody, So it's possible, but it's just so crazy improbable if following the statistics. But then again, circumstances change, so it's not like we're using this an even ruler, But you might have heard that tossed around on the TV or whatever, and that's what they're talking about. Finally, the variance and standard deviation are used quite often in inferential statistics. Okay, if you recall, inferential statistics is like predictive statistics, or also when you're taking samples and trying to make conclusions about the larger population. These uses will be shown in later chapters of this textbook. Yeah, so we'll get to that stuff. All right, so those are the two, two big pieces in this section: standard deviation and variance. Those are the most useful, most talked about, but there are others as well. So whenever two samples have the same units of measure, the variance of standard deviation for each can be compared directly. Okay. For example, suppose an automobile dealer wanted to compare the standard deviation of miles driven for the cars she's received as trade-ins on new cars. She found that for a specific year, the standard deviation for Buicks was 422 miles, and the standard deviation for Cadillacs was 350. She could say that the standard deviation in mileage was greater for the Buicks. She can say this because they're comparable, right? Buicks and Cadillacs, I mean, they're just talking about cars and trade-ins for a specific year, right? So a lot of things are being held constant. If you hold things constant, it's nice to compare things. But when circumstances change, maybe not so much. So what if, however, the manager wanted to compare standard deviations of two different variables, such as the number of sales per person, per salesperson over a 3-month period, and the commissions made by these salespeople? So those are two entirely different things. They're going to have two entirely different numbers, right? Different scales. So there is a way to deal with this, though. It is called the coefficient of variation. Okay, coefficient of variation. That's a way to kind of like put that number, that variance number, on an equal playing field, so that they're all kind of comparable. It's a statistic that allows you to compare standard deviations when the units are different. Okay, so this is usually read as CVAR, or the coefficient of variation. It's standard deviation divided by the mean. So the result is expressed as a percentage. And since it's expressed as a percentage, all percentages are comparable, right? At least in a sense. We shouldn't be subtracting and adding percentages because their denominator is going to be different. But anyway, the mean number of sales of cars over a 3-month period is 87. The standard deviation is 5. The mean number of commissions is $5,225, and the standard deviation is $773. Compare the variations of the two. Yeah, like what if I want to decide, like, which one of these varies more? Do commissions vary more, or do number of sales vary more? You would expect them to be kind of the same since one's based off the other, but we won't know until we look. So let's find the CVAR. We're dealing with, well, it shouldn't really make a difference since we already have the standard deviation. We're going to call this CVAR for population. So it's always nice to write the formula again. Multiplying by 100% is kind of silly since we all know how to interpret decimals. Okay, so we'll do it for the sales first. So CVAR sub S for sales. So the mean number of sales over the period is 87. Okay, so that's going to be 87. Standard deviation is 5. Okay. Let's do CVAR for commission, so sub C. That's they're going to be divided by 5225. Standard deviation was 773. Multiply that. Oh, I shouldn't put degrees. What am I talking about? Times that by 100%. All right, let's see what those numbers are. So 5 divided by 87. So that looks to me to be 5.75%. Okay. And then we have 773 by 5225. And that's 14.80%. Okay, so now we can clearly say that the commissions appear to vary much more. I would say almost three times as much as sales. So might as well write that out. We should get in the habit of writing our conclusions in full sentences. So, because statistics is useless unless you interpret it, right? So the commission, I should say interpret it correctly. The commissions are more variable than sales. There you go. Okay, so here's a nice little range rule of thumb. It's something you can hopefully carry around with you. All right, a rough estimate of the standard deviation. Like some calculations are done on the back of coffee napkins, okay? And this might be one of them really quickly if you're just discussing something and you want to come up with an idea about how variable something is or what the spread is. Really rough would be this, like saying the standard deviation, approximate standard deviation is equal to the range divided by 4. It's real rough estimation, but whatever. This is a rule of thumb to quickly approximate the standard deviation. It should not be used in place of the actual standard deviation. This is just to, in conversation maybe, or for quick judgments. Obviously, its accuracy varies. All right, guys, that takes care of 3.2. All right, we'll do some practice tomorrow in class, maybe some more examples. But that's that. Hope that wasn't so bad. I'll see you tomorrow. Hopefully, standing up's not so bad. It's just the period of time and the move. I don't know. We'll see what happens. Have a great day, guys. Turn in these notes for me. Be safe, and I'll see you tomorrow. If I can figure out how to turn this off, which is not looking good. My face.